Okay, in this lesson, we're going to compare theoretical probability to experimental probability. I know they're two pretty big words, but we can put it quite simply. Theoretical probability refers to what should happen in an experiment. Okay, that's what we did in the first lesson. When we were finding the probability of simple events, we were finding the theoretical probability. Theoretically, this is what should happen. And we're going to compare that today to the experimental probability, which refers to what actually happens when we perform the experiment. Okay. Ideally, the theoretical and experimental probabilities, they may or may not be the same. Okay. However, over thousands and thousands and thousands and an infinite number of attempts, those two, the theoretical, what should happen versus what actually happens, should become closer and closer to the same number. Right? For example, if you were to flip a coin, we know theoretically what should happen. It's a 50% chance to get tails, 50% chance to get heads. All right, so if I were to flip the coin 10 times, I should theoretically get 5 heads and 5 tails, right? Because it's a 50% chance. However, it's possible that if I actually do perform the experiment, it's possible that I get 10 heads in a row and 0 tails, right? But if I were to do millions and millions and millions of attempts, millions of coin flips over that time, I should get about half heads, half tails, right, theoretically. But it could differ from what actually does happen. So we're comparing, again, theoretical probability, what should happen, versus the experimental probability, which is what actually happens when we perform the experiment. Okay, and one more term here, we have uniform probability model. For an experiment to be uniform, each outcome in the experiment should have an equal probability of happening, right? It should be fair. So in a uniform probability model, each outcome has an equal chance of happening. So look at these two spinners here. Which of these two spinners has a uniform probability, where each outcome has an equal chance of happening? Okay, that would be this one. Right, we can see all the different spaces, the 4 different outcomes, have an equal chance of happening. Whereas this one over here on the right is not really equal, right? We could say that it's a higher chance to get a 2 or a 4 compared to a 1 or a 3, right? Just because the spaces are smaller. So the one on the left is uniform because they all have an equal chance of happening. Like if I were to ask you, will the outcome of the second spinner be an even or an odd number? Right? Yes, theoretically, it should be an even number, right? There's a higher chance of it being an even number. Does it mean that when we do the experiment itself, it'll be an even? No. Right? When we do the experimental probability, it may turn out to be odd. Right? But theoretically, we should land on an even number because they're bigger spaces. So let's start with some examples here. If I have a spinner with 3 equal sections, it's uniform, right? 3 equal sections, and we spin it 60 times. We sit there and we spin it 60 times and record every single one of the outcomes, right? Here's what we got in the actual experiment. 21 of those were green, 15 were blue, 24 were red. Now I know automatically in your head you're like, wait, that can't be right. They were 3 equal sections. They should all be spun the same. They should all should be landed on the same amount of times. Well, theoretically, yes, they should all be equal, but our experimental probability shows, oh look, our actual experiment was a little bit off from that. Okay, so let's look at what theoretically should have happened. Let's find the theoretical probability first. Theoretically, my number of favorable outcomes, there is one favorable outcome for red, right? We're looking for red. There is one favorable outcome out of 3 possible, right? So 1 out of 3 chance to spin a red, right? We had red, blue, green. That's 3 different outcomes. Our one favorable was red. So it's a 1 out of 3 chance to spin a red, or 0.33 repeating, or a 33.333% chance, right? Theoretically. And now we can compare that to what actually happened in the experiment, right? This one is what should happen, and this one is what actually did happen. So in the actual experiment, let's count. How many times did it land on red? That would be 24. Right? 24 red out of 60 total spins. So we're comparing the theoretical, what should have happened, a 33% chance of landing on red, compared to what actually did happen. Right? So if I were to reduce this one, divided by 12, to 2 out of 5, right? Or if I use my calculator, 24 divided by 60 is 0.4, or a 40% chance. So the thing here is that theoretically it should have landed on red 33% of the time. What should have happened was 33% of the time. It actually landed on it 40% of the time. Now, is that like ridiculous or out of this world or impossible? No. Right? But we landed on red. What this says is that we landed on red a little bit more than we would have expected to. That's all it is. Right? Theoretically, it should have been 33% of the time. It landed on red 40% of the time. Not the biggest deal. All we know is that it landed on red a little more than expected. Right? Or than what should have happened, right? Should have landed on there about 20 times. Landed on it 24 times. But again, we're comparing the theoretical probability versus the experimental probability, right? They could be different. If I were to spin this thing an infinite number of times, we would see that red comes up 33% of the time. Let's try another one. If we were to roll 2 dice, remember dice have a 1, 2, 3, 4, 5, 6 on each of them. If I were to roll 2 dice 20 times, okay, the outcome of 9 comes up 8 times. So out of 20 rolls, 9 came up 8 times. That's in our experiment, right? In our actual experiment, 8 out of 20 times, it came up as a 9. Okay, which reduces to, if I divide it by 4, to 2 out of 5, which is 0.4 or 40%. So 40% of the time in my experiment, 40% of the time it rolled a 9. Okay, and now if we go down to the bottom here, we can compare that to what happened, what should happen theoretically. Right? Theoretically, if I were to roll 2 dice, here's all my possible outcomes right down here. All of my possible outcomes down here. If I roll 2 ones, a 1 and a 1, it's going to be a 2. If I roll a 1 and a 2, it'll be a 3, right? 1 and a 3 is 4. If I roll a 4 and a 3, it's going to be 7. All right, so here's all my possible outcomes when I roll 2 dice, anywhere between 2 and 12. There are 36, if you count them all. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. There's 6 rows of 6. There are 36 possible outcomes when rolling 2 dice. Remember, theoretical probability is how many total outcomes are there, and then my favorable outcomes are my 9s. There's a 4 out of 36 chance that I roll a 9 when I roll 2 dice. You can see there are 4 favorable outcomes in here, right, out of 36 total, which reduces to 1 out of 9. And when I do 1 divided by 9 to find the decimal, I'll get 0.11, or an 11% chance. Theoretical. Ooh, it's a little bit different, right? There's theoretically an 11% chance that I roll a 9 when I roll 2 dice. But in my experiment, happened 40% of the time. So that's a lot more than we would expect. Is it impossible? No, of course not, right? I could roll the dice 20 times and roll 8 of them, 40% of the time. I could roll a 9. It's not what I would expect to happen. I would expect it to roll it 11% of the time. Okay, but we're just comparing what does happen in the actual experiment and comparing it to what should happen theoretically versus what actually does happen in the experiment. And again, over an infinite number of rolls here, we would see this number come back down towards 11%, right? We would roll 9 11% of the time. One more here. So let's consider the student store. Let's say the student store sold 24 candy bars, 11 ice cream, and 15 sodas. Okay. Next week, they predict that the store will sell 150 total items. How many of those can we expect to be ice cream bars? So based on what actually already happened, right, previously, I'm going to use that to predict how many ice cream bars will sell in the future. So let's consider what already happened experimentally, right? In the experimental probability, what already did happen, we did already sell 11 candy bars. Oh, not out of 150 yet. So we know in the experiment, they sold 11 ice cream bars out of 24 plus 11 plus 15 total items. So what this fraction here is we know last week they sold 11 ice cream bars out of 50 total items, right? They sold 24 candy, 11 ice cream, and 15 sodas. So 11 out of 50 of these were ice cream bars. Next week, we expect to sell a total of 150 items instead. So the question is, how many of those will be ice cream bars? Again, we're going to use the experimental probability, what did already happen, 11 out of 50 were ice cream bars, to predict if instead of 50 total items, we sold 150 total items, how many of those would be ice cream bars? Okay, and one way that we could solve this one here would be to, a few of you guys may have noticed this, to get from 50 to 150, I could just multiply by 3. 50 times 3 is 150. And if we triple how many total items we sell, we will probably triple how many ice cream bars are sold. So it should be about 33. If 11 out of 50 were ice cream bars before, then 33 out of 150 should be ice cream bars.